Hello, I'm Lee. In this video, we are going to look at some other options of trees. In the previous week, we explored the implementation of table by using a binary search tree. The binary search tree will give us a log 2 to n performance if the tree shape is good. But the problem with binary search tree is it could run out of shape pretty soon. For example, if I'm trying to add the following number to the tree, okay, how about let's start with 10. So I have 10 here. This node contains 10. And let's see, this is a 10. Then if I'm trying to add 20, this is a 20. And I'm trying to add 30, this is 30, and I'm going to try keep on going. You get the idea. So this tree is totally out of shape because it's not balanced at all. Remember when we talk about the balancing, we see the left tree and the right tree. The height, the difference between the left tree and the right tree's height shouldn't be greater than 1. But this one, the left tree's height is let's see 0, and the right subtree's height is 3. So it's totally out of balance. And when you have such a tree, it doesn't give you log 2 to n performance at all. Instead, it's just a linear linked list. You can see it's just a big O n performance plus the left no pointer that overhead. So it doesn't give you a good performance at all. So the tree's performance is closely related to the shape of the tree. So this week we're going to look at some other tree options, and those ones give us better performance like log 2 to n, and it always keeps a good shape. So the first tree we're going to look at is called 2-3 tree. So let's take a look. So similarly, I'm going to add the sorted number, because with the sorted number, the binary search tree get out of shape pretty soon. It's just go one way, and it forms a linear linked list instead. So now let's try 2-3 tree. So I add 10. So let's see, I add 10 here. I add 10. Okay, then I add 20. So 2-3 tree, a node can contain 2 data. And if it contains 2 data, it could have 3 children. So that's a 2-3 tree. A node can contain no data, that will be the no pointer, 1 data or 2 data. With 1 data, it could have at most 2 children. With 2 data, it could have at most 3 children. So now if I'm trying to add 30 here, I'm in trouble. So if I'm trying to add 30 here, because a node at most can only contain 2 data. So at this moment, what I will do is say, hey, this node is too crowded. It can only has 2 data. So I'm going to split the node and push the middle item up. So this is what we get. So 20. Alright, you see, perfectly balanced tree. So let's see, the idea of a 2-3 tree is when the node is getting too crowded, you split it and push the middle item up. Alright, let's keep on adding. So if I'm trying to add 40 here, so you add 40 here, and this node is alright. And if I'm trying to add 50 here, then you know we have to split at this moment, because a node cannot contain 3 data. So how to split? We push the middle data up. So now here's a picture. So at the root node contains 2 data, and alright, so you see the left subtree will be less than the smaller item. The middle tree will be between the smaller item and the bigger item, and the right tree will be bigger than the bigger item. So that's a 2, 3 tree. Now if I'm trying to add 60, okay, here, that's fine. If I'm trying to add 70 here, let's see, we're in trouble. You know the drill. Push up the middle item, and so 60 comes here. All right, 60 come here. We say, all right, this is too crowded again. What do? Keep on splitting. Push up. Okay, now this is the final tree we're looking at. So 40 is pushed up. That's a new root. And 20 and 60 and 10, 30 and 50. Now look at the current tree. It's always balanced. Unlike the binary search tree we have at the beginning, like 10, 20, 30, 40, 60, 70, that's a linear linked list all the way to the right. This is a perfectly balanced tree. So this one will give us a log 2 to n performance. So that's 2-3 tree. Let's take a look. So when you insert an item in the 2-3 tree, just like the binary search tree, you always add it as a leaf. But when the leaf is too crowded, you push up the middle item and split the node. So you split the node, and when the leaf is too crowded, you push up the item, you split the node. You can keep on doing this. And you see, you only increase the height. You see, we have 2 height increase. This is height 1 to height 2. So you only increase your height at the root. When you say, okay, there's no place to host that new node, we have to split and push up middle item, then you increase the height. So this is one place to increase the height, and this is another place to increase the height. When you increase the height, you always increase it at the root level, so you always get a balanced tree. So that's the idea of 2-3 tree, always balanced, guaranteed log 2 to n performance. Now let's take a look at how to delete something from the 2-3 tree. And just like the insert, we want to keep the shape of the tree balanced. That's the idea. So for deleting some nodes, we go the opposite way. Remember when we add something, we say when it's too crowded, we split. And when we do deleting, when it's too empty, we merge. So the totally opposite process. So let's take a look at the deletion algorithm. So now I have a tree. Let's see. How about I have 20 here, and 10, and 30. How about I'll give it 2 data here, make it 3 nodes. And how about make this one, let's give it 40, 50. The 60 and 70. Alright, so for deletion algorithm, it's just like a binary search tree. We always delete at the leaf, the bottom layer, which is a leaf. If it's not a leaf, we find the in-order successor. For example, if I'm trying to delete 20, I'm going to find the in-order successor, which is 30, and move 30 up and try to delete 20. So exactly the same algorithm. Like if I'm trying to delete 50, I'm going to move 60 up and trying to delete this one. So like the binary search tree, we always delete a leaf. So I'm not going to go through that step. So I'll just show you how to delete some node at the leaf level, because you can always make deleting any node as deleting a leaf. Alright, so now let's take a look. So if I'm trying to delete 70 here, it's no trouble, because this is 3 nodes which has 2 data. So you just delete this node, your tree shape isn't changed at all. So now if I'm trying to delete 60, I'm in trouble. because this node is empty now. You see, this is an empty node. Okay, what do we do? So now here's the algorithm. When you're trying to delete an item in a leaf node, if that node has two data, then you're lucky. You just go ahead delete that data. You don't have any work to do. But after the deletion, if the node is empty, you know what to do. Let's take a look at this one. So I'm going to look at my sibling and my parents, and this is what I find. My sibling here, this is a sibling here, has two data, so that's good. I'm going to redistribute data between this sibling, parent, and this node to be deleted. I'm going to redistribute data so I can move 35 up and 50 down. So these three data, 30, 35, and 50, I'm going to redistribute this data among these three nodes. So this is a picture. So that will be 20, 30, and 35. So move 35 up and 50 down. So you see the redistribution is this data, and this data. Now 30 is still here, 35 is moving up, and 50 is here. So you do the redistribution. Okay, this is still a balanced tree. Now let's see if I'm trying to remove 50. Now I'm in serious trouble. So this is an empty node, and I'm looking at my sibling and my parent, and I cannot do some redistribution anymore, because if I redistribute, this will be too many children. If I get 35 down, 20 cannot have 3 children. 20 is a 2 node. It can only have at most 2 children or 3 children. So at this point, it becomes too empty. I'm going to have to do something called a merge, the opposite of split. I have to merge. So when I do the merging, that means instead of 3 children here, I'm going to become 2 children, and I have to move down one data. So we're going to move 35 down. So this is a tree, how it look like. So 10 and 30 and 35. So alright, still a balanced tree. So that's an algorithm for deleting an item from a 2-3 tree. So the first step is to find the in-order successor. If it's not a leaf, so you always delete at leaf level. And if this item is sitting in 3 nodes, that means you don't have to do much. You just go ahead delete the item. And if this item is sitting in just a 2 node, which means that's the only item in the node, you're going to look at your sibling to see if they have some data to spare. Then you do some redistribution. And if your sibling is pretty empty too, like only has 1 item in it, then you're going to have to go through the merge process. So the merge process will be, okay, if it's a 3 children one, you have to make it 2 children and move down some data from your parent. And as you can imagine, this is a recursive operation. So if at the end the root becomes empty, you just delete the root, and you got the height is decreased by 1. So as you can see, for 2-3 tree, when you insert item in it, it only increases the height at root, and when you delete item, it only decreases the height at root. It's always balanced, log 2 to n performance. Thank you.